Well, good morning, everybody. At least good morning here in the U.S. on the East Coast, in the exida headquarters in Sellersville, Pennsylvania, just a little bit north of Philadelphia. My name is Iwan van Beurden, and I will be conducting the webinar today for you. And we're going to talk about an exSILentia use case. Specifically, we're going to talk about final element proof tests and one of the new features that we've added in our latest release. And as most of you already know, the more extensive your proof test, the higher the proof test coverage, the longer you can run in between with longer proof test intervals. So that's what we're going to talk about. We're going to have some background information before I'm going to open up the tool and show you the feature. The feature is very straightforward, I think, and pretty neat to look at. But it's good to have the background information first. I assume that most of you are familiar with our webinars, so you know that audio is provided via the GoToWebinar application over the internet. Make sure your speakers are enabled, and that you should also be aware that you can talk, but I won't be able to hear you. The application has muted your microphone. So if there's any questions throughout, feel free to use the question tool, which is on the right-hand side of your screen. At least in my case, it's in the GoToWebinar widget. You can ask a question, and I'll read that question and try to answer it. And depending on the questions, we may need to do some question answering after the webinar. In some cases, I'm able to address everything during the webinar. But feel free to ask questions. So my name is Iwan van Beurden, and I am CTO, Director of Product Development here at exida. I do a variety of things when it comes to support for end users, anything from facilitating your PHA all the way to reviewing your decommissioning plans. I work with manufacturers who are trying to be compliant with the IEC 61508 standard, and I'll try to help indicate where there may be a gap and where they need to improve their overall development processes. And I'm involved with some of the certification activities, both for OEMs as well as end users. In some cases, we do certify plans to indicate that they have been developed according to 61511 as a deliverable, basically from an engineering contractor to the final owner operator of the plant. But majority of my time I spent within the product group within exida, and I'm responsible for the development maintenance of the exSILentia software. I'm a member of the 61511 committee, a member of the 84 committee. So I'm pretty active when it comes to functional safety. When we look at exida, we see basically a group of people that you can somewhat divide into three subgroups that form the foundation, the pillars upon which exida is founded. And we have a group of people that are very active in the certification and assessment region. You're probably familiar with many products that are being certified by exida, as well as individuals when it comes to the Certified Functional Safety Expert program. We have a group of people that are very active in the lifecycle services, and again, do everything from, let's say, process hazard analysis all the way to proof testing, decommissioning. And then obviously the most important group is the product group, because that's what I'm working in, where we help develop tools for use by end users as well as manufacturers to support their overall lifecycle activities. And obviously the exSILentia software is one of our key products when it comes to these enterprise tools. As a company, we have many offices around the world. We have many different projects that we've worked on around the world, from the Gulf of Mexico to Australia, from the automotive industry in Europe to alarm rationalization in South America. So we're just we're very active around the world with many offices and many different teams and projects. So that is exida in a nutshell. So let's start with looking at this proof testing and specifically for the final elements. So in order to ground us, let's start with a overview of the safety life cycle. And I assume that everybody is familiar with it. This is basically the life cycle as you can find it in IEC 61511 or ISA 61511. And it's providing a method to analyze, implement, and maintain a safety instrumented system, all the way from a project scope definition to decommissioning. When we talk about proof testing, we really are looking at the first part of the life cycle. We are looking at defining the proof testing is what I'm talking about. When we define our proof testing, our intervals, the types of tests that we need to do, we're in that design and implementation phase. So that's the upfront part of the life cycle, where in the analysis phase we do the PHA, the LOPA, the SIL selection. In the design and implementation phase, among others, we do SIL verification and the various tasks that are involved. When we look at the process hazard analysis, we brainstorm the possible hazards, the layer of protection analysis, we identify protection layers, SIL selection, we determine the SIF integrity requirements, the safety requirement specification, we document all the safety instrument and function design requirements, and then in the SIL verification, we determine if our conceptual SIF design is adequate for addressing the requirements, but we also define the maintenance and testing strategy, and that's where we're going to be focusing on. Then obviously after that, when we operate the plant, we need to record proof tests, we need to record failures and so on, and we're not really covering that here in this webinar. Obviously within the exSILentia software, there's a strong component SILstat that addresses that, but we're focusing on proof testing, or basically defining the proof testing strategy. So when we talk about the SIL verification, and when we talk about calculating what basically my achieved safety integrity level is, there's 3 different SIL levels that we need to take into consideration. There's a SIL level based on the average probability of failure and demand. There's a SIL level based on architecture constraints or minimum hardware fault tolerance. There is a SIL level based on equipment capability or systematic failure integrity, basically. And exSILentia in the silver module does take care of all those individual components. And here's just a simple overview as to the different parameters that are impacting the respective SIL levels. And when it comes to proof testing, we can see that the proof testing is impacting that probability of failure. So that's what we'll be focusing on in the webinar. We're not going to really address the architecture constraints or systematic capability. We're going to look at this proof testing and the associated probability of failure. So one of the things that we need to understand when we look at these proof testing and reasons for proof testing is we need to understand what the types of failures are. And within functional safety, we distinguish 2 key failure modes. We talk about dangerous and safe failures. And a dangerous failure is a failure that will prevent a device from responding to potential dangerous condition. And a safe failure is a failure that will cause a device to go to the predefined safe state. So dangerous failures are preventing our safety function from performing from performing its task, whereas the safe failures will initiate the task even though there may not be a demand from the process, even though there may not be a reason to perform the safety action. And we talk about the dangerous failure rate as the lambda D and the safe failure rate as lambda S, respectively. So what does that look like? Well, assume normal operation. I have a furnace, fuel is flowing through the pipe, and if everything is happy, I want to open up my valve and have just fuel going through it. If for whatever reason I decide that I need to stop the process, I want to close my valve. Very straightforward. If for whatever reason, for example, the valve stem is stuck, the valve remains open and I'm not able to achieve the safe state, that will be a dangerous failure. Now, by itself, that is not necessarily a problem. It's only going to be a problem if there's a demand from the process. So only if my process runs out of control and I need my safety function to perform, that's when that's when we will have an issue, and typically that will lead to a kaboom. The safe failures on the opposite are, that could be an actuator has a leak in the pressure chamber, therefore the spring forces the actuator close. Obviously, that is resulting in stop of fuel flow in this case. It's not dangerous, but it stops the process. So we have availability issues at that point, and we typically tend to look at monetary impact for those items. From a functional safety perspective, from a standard perspective, we're not that interested in safe failures, as long as those safe failures do not cause a hazardous condition elsewhere in the process. But obviously, from an operational perspective and an overall availability perspective, production capability, we are very interested in that. These safe and dangerous failures are then further divided into two categories, detected and undetected. And what we mean with that is, are there any automatic detection mechanisms in the product or in the safety instrument of function that can reveal failures during normal operation? And if those failures are revealed, we call them detected. And if these failures are not revealed, we call them undetected. So we end up with safe detected, safe undetected, dangerous detected, and dangerous undetected failures. Of those four categories, the dangerous undetected failures are the ones that we worry about most. Dangerous undetected failures are failures that will prevent our SIF from performing its intended function, and we don't know about it. Now, if we have a dangerous failure, obviously that's not good, but if we have detected that failure, then we can take action. We can perform a repair action. If we don't know that it has failed, then obviously the operator doesn't know, or the maintenance person doesn't know that something is wrong, and we would simply rely on the SIF, whereas it's not available. So when we look at the overall safety integrity of a safety instrument of function, we will see that it's primarily dictated by those dangerous undetected failures. And in order to address that, we are performing periodic manual tests to reveal failures, dangerous undetected failures, that are not revealed during normal operation. So that's the objective of a proof test. We're not really trying to prove the functionality of the safety instrument of function. We're trying to detect any dangerous undetected failure that is not revealed during normal operation. Now, quite often those overlap. Quite often, in order to detect those failures, you need to prove the functionality, but it's not 100% the same. We just want to find those failures that are not detected during normal operation. And what does that do? Well, you've probably seen a similar chart where we see PFD as a function of time increasing, and then if I get my my spotlight here, if we would not do any testing, this chart would just simply keep going up, and eventually we would reach to probability failure of 1. But because we do proof testing, we will detect failures, and we will go back. The probability of failure will reduce, and we get a new sawtooth, so to say. In functional safety, the probability of failure, we can see that in low demand applications could behave like this sawtooth. So instead of looking at the maximum or the minimum, well, this would be the maximum, this would be the minimum, we're looking at the average. And obviously the average is then this dotted line, and that is the one that relates to a particular SIL level. So that's how proof testing impacts PFD average. Okay, so let's look at that in a little bit more detail. There's a couple of things here: proof test frequency, proof test effectiveness, proof test coverage. So let's look at the frequency first. Very simplified equation here, which obviously wouldn't yield the graph that we saw on the earlier slide. This simplified equation simply says that the average probability of failure in a month is a dangerous undetected failure rate multiplied with the proof test interval divided by 2. So just imagine that I double my proof test interval. Obviously, the average probability of failure will be doubled. Or if I reduce my proof test interval, my average probability of failure will be reduced. PFD increases as a function of time, and the interval will have an impact on that. And we can see that here in these screenshots that you see here. We have on the left-hand side, we have a system where we do a proof test once a year. On the right-hand side, we do a proof test once every 5 years. And we can see the sawtooth. Let me get my spotlight again. We can see the sawtooth, very, active on the left-hand side, and very, not as active on the right-hand side. And we see that the average probability of failure in the month on the right-hand side is a lot closer to the SIL1 boundary than on the left-hand side. So, testing has an impact on the probability of failure. And in this case, I think we assumed 100% proof test coverage as well. So it's only looking at the frequency. But you can see that a little bit of change on the right-hand side, and we're no longer meeting SIL1. There's a little bit of change on the left-hand side, and we would still be nicely in the SIL1 boundary. So one could conclude that the more frequent you're testing, the better. And yes, from an average probability of failure on the month perspective, that is absolutely true. The more frequent you test, the more likely it is that you will reveal dangerous undetected failures. The more likely it is that your system will be in operation or capable to operate when it needs to operate. However, there of course is a balance. We could say, hey, you need to test every month. And if that is a manual test where the process needs to be shut down for continuous operating principle, that is not really ideal. And often we see in initial requirement specifications that customers would like, let's say, a 5-year or 6-year proof test interval because they don't want to shut down. They don't want to stop the process in order to perform a test, which is reasonable when we all need to make sure that we can pay the bills at the end of the month. So we need to find a balance, and that balance may not be as trivial when it comes to the test frequencies. We'll see that when we look at different coverages, different extensiveness of tests, that there are some trade-offs that we can make. So let's look at that. Proof test effectiveness. So that same simplified equation that I showed earlier, dangerous undetected failure rate times the proof test interval divided by 2 in order to calculate the average probability of failure in the month, we can extend that equation and include proof test coverage in it, or proof test effectiveness. And we can see here a coverage factor of the proof test that is being multiplied with the dangerous undetected failure rate times the test interval divided by 2, and then a portion of the formula where we do 1 minus the coverage factor, so everything that's not revealed, times the dangerous undetected failure rate times the mission time, the time that the SIF is in operation, divided by 2. Is in operation before all the components in that SIF are being either replaced or completely refurbished, that it's really as new. So we can see that once we start to take into consideration that coverage factor, that coverage factor can have a significant impact. If the coverage factor is very low, and let's say my proof test interval is 1 year and my mission time is 10 years, then the majority of, let's say, the failure rates are on the right-hand side of the equation, get multiplied with 10 instead of multiplied by 1, and it can become pretty dominant on the right-hand side quickly, just because that interval is a lot longer than the typical proof test interval. So the more extensive the proof test, the more effective the test, the higher this coverage, the lower the right-hand side portion, the more dominant portion because of the extended interval, the lower your average probability of failure in the month. And we can see that here for a scenario where we're testing once a year, and on the left-hand side, it looks like we're assuming 100% proof test coverage, which would be unrealistic. It's typically impossible for an end user to really achieve a 100% proof test coverage. Though some manufacturers may claim that. I've seen safety manuals where it's stated that you as an end user need to test for all possible fault routines, and thereby you can claim 100% proof test coverage. Well, yeah, that's true, but I don't know how, as an end user, you can initiate memory corruption and do a certain test that would indeed get you that 100% coverage. Anyway, on the left-hand side, we're assuming that 100% proof test coverage. On the right-hand side, we don't have 100% proof test coverage, and you see that the PFD chart, as a function of time, will slowly increase. So you see a increasing line that you actually, I think I can draw that here with this pen. You can see that the line is slowly going up with time because the portion of the system that is not detected, the failures that are not revealed during normal operation, is starting to increase, starting to become more dominant. Think of that multiplication with that mission time. Now, in this, in the more accurate modeling, there's not that multiplication. There's just accumulation in let's say, absorbent states. But that goes in a little bit too much detail for the webinar here. So we can see that proof test effectiveness can have quite an impact. So then the question, of course, is, well, how do we get that proof test effectiveness? How do we get that coverage? Well, many manufacturers, well, if they are IEC 61508 compliant, if they are have a certified product, must have a safety manual. That safety manual could be a separate document, could be part of the standard operation and maintenance documentation, but there are certain aspects that need to be recorded in that safety manual. And one of those aspects is a proof test and associated proof test coverage. So I can go to a transmitter manufacturer and I can ask them for their safety manual, and it will tell you a proof test with a proof test coverage. And what you will typically see is proof test coverage in the 90+% for transmitters. Usually there are tests that are relatively easy to perform by you as an end user that can get very high coverage factors. But if we look at the finer elements, it's a little bit different. You may find different tests ranging from a partial stroke test, a full valve stroke test, or maybe a full valve stroke test and a leak test at operating conditions. So it's very clear that for partial tests where we need to move the valve 5 to 10% of the total stroke, we will have a coverage. We will be able to detect if the stem of the valve is stuck. If we do a full valve stroke test, we obviously will detect that failure, but we will also be able to detect if there's anything else blocking the valve from closing completely. If we go to the fourth test here, if we include a leak test, we can also see how well the seats of the valve are still in operation. And then at operating conditions, we will see the actual pressures on the valve and we can see how it behaves. So there is different types of tests with different levels of effectiveness, very easily to be seen for a fine element. And you may perform a SIL verification calculation and you may come to the conclusion, you know what, that full stroke is all I need. I need a SIL 1 safety function, and full stroke is everything I need. I test once a year and I'm happy. Whereas if you may get to a point where, you know what, we want to test once every 2 years or once every 5 years. Can we go with a test that, can we go with a longer interval? And maybe as a trade-off, we have to do a more extensive test. The leak test requires additional equipment, or requires that you can measure pressure before and after the valve. And is it really worth that extra? Is that really worth that extra money, so to say, when it comes to running that test? So those are different questions that we have to ask when we're designing our safety instrument function. I just wanted to point out, I see a couple of questions here. I'll come back to those in a little bit. I think it makes sense to address those a little bit. So we have these trade-offs. The more extensive the test, you expect to detect more failures. Therefore, but more extensive means it's probably going to cost more. What do we want to do? So how do we get that? Typically, if I look at the certification process that we as exida tend to do is we perform a failure mode effect and diagnostic analysis. And when we perform that analysis, we have a very detailed overview of all the different failure mechanisms in a device, and we can see if we perform a certain test what the failures are that will be detected or will be revealed by that test. So we can very accurately predict what that proof test coverage is. That's part of our certification process, but as I said, typically manufacturer is documenting that stuff in their safety manuals. And here I have an example of different proof test effectiveness for a final element assembly consisting of a solenoid valve, a spring return Scotch yoke actuator, a trunnion ball valve, and some mounting and coupling. And we can see the 5 different tests that we defined. So the proof test 1 is not really a proof test, but it's the first test. It's the partial stroke test. PT2 is the full stroke test. PT3 is the full stroke test at operating conditions. PT4 is the full stroke and leak test. And PT5 is the full stroke leak test at operating condition. And we can see that of the dangers and detected failures of the solenoid, we will be able to detect certain failures if we do a partial stroke or full stroke, but we will detect more failures if we do it at operating conditions or if we do a leak test. And the same thing with these other components. So valve, excessive force, certain failure rate, loss of drive, a certain failure rate, and it's all the failure modes here are all expressed in the failure modes of the entire final element assembly, not the individual components. It's all expressed in the one common denominator, basically for the different tests for the different components. Sorry, I was distracted by another question. And again, I'll come back to those questions in just a bit. So what's that impact of proof test frequency and effectiveness? And I'm going to use a very simple safety function. We're going to use 3 transmitters, FOTA 2 out of 3. We're going to use a generic SIL 3 certified PLC. We're basically using equipment where the sensors and the logic solvers don't really have an impact on the overall safety function, that we can really focus on what does the final element do. But it would be wrong to just start calculating PFD average values for a final element and then concluding certain SIL levels that we achieve, because SIL level is obviously part of the overall safety instrument function. But then our final element is going to consist of a single floating ball valve, which is driven by a spring return rack and pinion actuator, and that is operated by a 2-3 port pilot operated solenoid. So that's our final element assembly, and that's something we model. So we can look at different tests and the associated proof test coverages, and we can then determine the impact on the PFD average. And again, for the test procedures, we fix the transmitters at 5 years proof test interval, the logic solver at 5 years proof test interval, and for the final element assembly, we chose a couple of different proof test intervals just to see what the impact is. And then we're using these different tests descriptions to look at it. Within the exSILentia software, we have the Safety Equipment Reliability Handbook database embedded. And for more and more devices, we have different proof test coverage factors available. And here is basically the data for a generic floating ball valve. And you can see there is data for, let's say, normal operation and data for partial stroking operation. So that's test 1. So we have those different coverages as part of 2 sets of failure rates. And then for the different proof testing, we have the applicable proof test coverages. So we have a proof test for a full stroke, a proof test coverage for a full stroke at operating condition, proof test, full stroke with leak test, proof test, full stroke, leak test at operating condition. And for more and more devices in our equipment database, we have this information available. And if you will look at older devices where maybe the analyses were not including operating conditions and leak testing, you may just see one proof test coverage value. Our intent, of course, is that all these devices are updated over time. It's part of our regular recertification or reanalysis of particular equipment, and has all the, so that they will have all the proof test coverages that we will be using. So that's just an example as to where the data is, and when I open the tool, I will show you where we can find that data. And then we can run our calculations, and we can see these results in just a bit in the tool as well. I think I'm going to open up the tool in the next slide. But if we would say, hey, we want to test once a year, and we want to do just a, let me get my highlighter, and we want to just do a full stroke test, we get a certain probability of failure for our safety instrument function. If, however, we do a more extensive test, we can extend our proof test to 2 years, and we're still having a better risk reduction, a lower probability of failure in the month if we do that full stroke leak test at operating condition. So we can see that doing a more more extensive test, we have a better safety performance if we test less frequent. Now, I'm not suggesting that you shouldn't be testing frequently, but you can see that the more effective your test is, that the better your probability of failure is going to be, the higher your risk reduction. But it also allows you to extend that over a couple of years then. And you could, if we're just trying to achieve a SIL 1, you can see that we can go 5 years with this particular test, with this extensive test, and we're still in the SIL 1 range. So, and we're not, it's not at the border, we're in the middle of the range. So it's not like we're trying to get by our teeth, but we're solid in SIL 1 range. Now you could argue, hey, that's also the case for the cheaper tests, and there's always a lot of different factors involved, but you can see that there's quite some impact here on the calculated results. So what does this look like in exSILentia? So let's open up the tool, and I have a project ready to go. Let's go to the dashboard. In this project, I just have a couple of safety functions. They're actually copies of each other. They're all the same safety functions, but with different tests. One thing that you want to make sure is that all your devices are up to date. So in the widgets here on the dashboard, there is a widget for equipment update. And as we are adding more and more coverage factors, there may be a good reason for you to update the equipment that you are having in your project. So you can just simply show all the devices. In my case, I'm up to date with everything, but then you could still force the tool to say, I want to update all the devices to the latest data base. So so you make sure that you have all the proof test coverages available as much as possible. We can then also open up our library, and we can go to the device models. And for example, here on the floating ball valve, if I look at that floating ball valve, open up the, let's say, the data sheet for it, you can see a lot of information. Let me get the highlighter again. You can see that we have clean service, close and trip, operation, full stroke, no partial stroke testing, and we see failure rates and associated coverage factors. Now we have the same set of that, but then for partial valve stroke testing with a set of failure rates. Then what if we need tight shutoff? What if no partial stroking with tight shutoff, tight shutoff with partial stroking, open on trip with partial stroking, without partial stroking, and so on. And then we have severe service. So there's a lot of different components, a lot of different factors here involved. We can actually, if I go back to my mouse or cursor, you can see there is also different SSI data available So we have SSI2, which tends to be our typical default, but SSI0, SSI4, I think, as well. So there's a lot of different data sets available for just this one item, generic floating ball valve. I'm not talking about SSIs today, but I just wanted to share that with you, that we have all that information in our equipment database. Similarly, if we would like to look at the solenoid, we can open up the data sheet for the solenoid, and we can see the different SSIs, but there's basically one set without partial stroking and one set with partial stroking, and different coverage factors. And for the solenoid, there may not be that much difference between the type of test that we're running, because the solenoid is going to be stroked completely. And it may be more evident in the valve, but those are all things to take into consideration. So then if we go to the Silver tool, we can see a total of 5 safety functions that I modeled, with PT1, PT2, PT3, PT4, and PT5, all containing the same equipment. And the only oddball here is really the first one, where as you can see, this is the partial stroke test. I obtained the partial stroke test coverage that you can see here. I obtained that by enabling the partial stroke test interval, but because we're just considering the partial stroke test as a, let's say, a proof test, I put the coverage factor up here in the proof testing area. So that's really the only oddball out. But if we go to the full stroke test, the regular PT2 test, we can see that, okay, we have an interval once a year, no leak testing, and we're not doing it at operating conditions. So these 2 checkboxes are not checked, and we can click on our proof test coverage calculator, and we get a suggested proof test coverage of 77%. And let me just get the spotlight here, and notice that the coverage factor that we're using is 52.9%. So that is for a, let's say, full stroke test for a floating ball valve. Oh, yeah. So now let's go to that same test, but running it at operating conditions. So we see the exact same equipment selections, the exact same items. The only difference here is that the at operating condition checkbox is now checked. And then if we click on the proof test coverage calculator, we can see a different proof test coverage being used for that floating ball valve. We can see here it's now 58.6% instead of the 52.9 on the let's say normal test without operating condition. And we can use that coverage factor here. And then for the leak test scenario, where we do a leak test in addition to the full stroke, we can see that the leak test is now selected. And when we click on proof test coverage calculator, we can see here a 52.9% proof test coverage for my final element, for my valve to be specific. So, leak test is checked, and we see a higher proof test coverage. And the tool takes that into consideration and calculates a 93% proof test coverage for the combined solenoid actuator valve assembly. And then lastly, if we go to scenario where we do the leak test at operating condition, so both of these check boxes are checked, we can see that when we click on the proof test coverage calculator, now that our floating ball valve allows a 98.6% proof test coverage. So the tool automatically knows what the coverage factors are for the different tests. You as a user just simply indicate the types of tests that you do. Is it a full stroke? Is it a full stroke at operating condition? Is it a full stroke and a leak test? Is it a full stroke and leak test at operating condition? And based on that, the tool will then determine the appropriate coverage factor, and you can calculate the overall proof test coverage for your valve. And we can see here that for 1 year interval, that would lead to a 1.37 E-2 result. And we can see that if we would extend that to, let's say, 5 years, and rerun the calculation, we can see that that then updates to a 4.4 E-2. Still in the SIL 1 range. We're still good for SIL 1, but with a obviously with a little bit higher probability of failure demand. So as you can see, these coverage factors are embedded in the software, embedded in the equipment database. Just 2 clicks, and you can account for those particular items. So that's how it looks like in exSILentia. Very straightforward, and that's one of the new features that we released not so long ago in our 4.8 release of exSILentia. In addition to that, we released a proof test generator module, which will basically help you generate proof tests. And one of my colleagues will be doing a webinar on that shortly. But that's also a very exciting item. And in this case, we're focusing on the coverage factors, and that's all covered here in that proof testing block. Only for final elements, of course, because that's where the different tests apply. All right. So with that, we've reached the end of the webinar, and it's time for questions. And I have a couple of questions here, so I'll go through them. So one question is it essential to carry out partial stroke test of a shutdown valve in SIL 2 loops? It all depends. If we go back to the software here and we go to this most extensive test, obviously let's go to 1 year as well, 1 year test interval for now. Obviously we're not meeting the SIL 2 requirement that I put in here. So in this case, with the equipment that I've selected, keeping in mind this is generic equipment, and our generic equipment is intended to cover around 90% of what is available in the market. So if you find a specific floating ball valve from a specific manufacturer, you may have lower failure rates. Generic data is always intended to be conservative. But let's say this is what it is. Obviously, I'm not meeting SIL 2, so there's different options. I could add redundancy. That would not be the most cost-effective, probably. I can also include partial stroke testing. So I don't know if this is going to change anything, but let's say we're going to do our partial stroke test once a month, once an hour. We say we're going to initiate it automatically. We use data from our equipment database for the partial stroking. Now keep in mind, I need to update our proof test coverage because now certain failures will already be revealed during normal operation. For example, that stock stem will be detected during normal operation as part of the partial stroke test. So our proof test coverage overall will go down, but our overall achieved probability of failure, let's see, would be good enough for SIL 2. So I cannot answer your question with, do we always need to do partial stroking for SIL 2? It really depends on the equipment that you're using. You could even assume that you replace the valve once a year, and thereby having 100% proof test coverage. Now that's probably not going to happen, but you could make that assumption. You could end up with a lower probability of failure. In this case, with this data, yes, you would end up with needing to do something extra to get a higher risk reduction. But it's not a rule that it always needs to be that way. And here's also talking about a turnaround time. So that's actually something I didn't really focus on. So in this case, we've assumed a 15-year mission time. So we've assumed 15 years until everything is replaced. If you meant we're going to do the full proof test once every 5 years, we can change that here. And I don't know what it's going to look like after that, but we're dropping significantly to the SIL 1 range again with this equipment, and there may be some other factors that we may need to take into consideration. Also, I'm assuming that our partial stroke test operates the solenoid. It may not, so we may not. We may need to exclude the solenoid from the partial stroke testing, and that may again lead to different result, but probably not good enough for SIL 2. Now, for again this equipment, manufacturer specific equipment, you may be better off. And again, our generic data tends to cover around 90%. of what is available in the market, meaning that 90% of the equipment that you will find in the market with specific failure rate data will be better than our generic data. Then it's a more technical question with regard to the timing of the valve closure, and that is actually something that will be interesting to look at. Okay, sorry, I dropped the audio there for a minute. It would be interesting to look at that with a specific manufacturer's safety manual. There may be a requirement in there to perform a test and time the actual operation of the valve. So that is depending on the test that's required, or it may come from overall actuator. How fast can we perform? And you may need to verify that with the expected response time of the fine element. So yes, timing could be an important factor in the proof testing. Then there's a question here: how do you incorporate partial stroke testing that is typically done at a more frequent interval? I showed it to you right here. It's very easy in exSILentia. You just simply say, hey, I do partial stroking. You specify the interval. Oh, and what does that mean to your PFD chart? Okay, you can't really see here. So I'm going to increase the interval to 6 months just to make sure that the graph shows a little bit better what is actually happening. So if we run that calculation, you can see specifically, if we would go to the fine elements here, we see once every 5 years in this example. Once every 5 years, we do a more rigorous proof test. Once every 6 months, there's a smaller proof test going on. So the simplified equations that I showed on the slide could be updated to add another factor for partial stroke testing. In our case, with our calculation engine, Markov model base, it's a real-time calculation, or it's a discrete time calculation. We account for what's the probability failure at every point of time. This chart that you see here is just a collection of calculated results that happen to be a line. Pixels. Every pixel is calculated, and that is that's what we're showing here. So you can see that partial stroke testing is accounted for in your calculation. That's easiest to see in the charts. This is a good one. How do I come up with these proof test coverage values if it's not part of the safety manual, or if the manufacturer doesn't have that information? Well, the easy answer there is have the manufacturer contact exida. Obviously, we can help the manufacturer obtain that data. If the manufacturer is not willing to do that, or not willing to help you get that data, then use generic equipment. Again, assuming that the particular manufacturer you're looking at is part of the, let's say, 90% in the industry that is better than what we've assumed for a generic. If you use generic equipment, you are you're on the safe side. You can use the respective coverages there. This is another interesting one. This is statement here is: I thought that the proof test interval was defined as an end-to-end test, meaning I test my sensors, I test my logic solver and a fine element as one loop. And obviously in my example, I'm focusing on just one test of the fine element. It all depends on philosophy. Some customers want to do an end-to-end test, and most of the time that end-to-end test is then also looking at, let's say, the application logic. And some customers want to basically test the entire application logic, every proof test. You could argue, however, that the objective of a proof test is to detect dangerous and undetected failures. And the change of the application program, which is then basically being looked for, is really a systematic issue. I'm not saying it's not it couldn't happen, change the application program. But theoretically, it's not part of the typically objective of the proof test, which is to reveal dangerous and undetected failures. One of the things that a user could do is they could simply look if they have a safety PLC. The application program typically has some kind of identifier, maybe a CRC code. They could just simply see, hey, what is that CRC code? Is it the same at the end of commissioning, installation, etc.? When we started to introduce the system, is it the same at this point when we do the proof test? If it is the same, then your application code hasn't changed. And you could just limit yourself to looking for dangerous and undetected failures in the logic solver, and you can separate them. You don't have to, you don't have to do complete loop-to-loop tests. For example, if you have a burner system and you have many different scenarios where every action is close the valve, why would you be closing the valve every time? You can just simply, test if the valve operates once and take credit for it in all the order functions. So a more segregated proof test could be beneficial just from a overall maintenance requirement perspective, but also better on your equipment. Instead of slamming that valve shaft over and over and over again, you just test it once. But it's philosophy. Some companies really do want to do an end-to-end test, and other companies are very adapted to just testing those pieces that really need to be tested. Can we select different proof test coverage for the solenoid and the main valve? Yes and no. So in this case, I am selecting equipment from our equipment database, and in my proof test calculator, that is where it will get the proof test coverage values from. If you have a user-defined item, so I can go to our data library real quick. I go here to the device models. I'll add a device model. Click on view of that device model. I can say this is a, let's see, where are we? This is a valve. I can specify failure rates and I can specify proof test coverages. So I have the ability to specify proof test coverage for a user-defined item directly in our tool. Alternatively, I can overwrite this value. If for whatever reason I think it should be 90%, I could just enter 90% right here in the tool. Now that assumes that you've done that this quick calculation here, weighted factors on the different components in your finite element group, and end up with a particular value that is applicable for you. So you cannot change the values that the tool will get out of our equipment database, and it's using in this calculation. But you can overwrite the result, and you can add your own equipment data as applicable. The assumption on the partial stroke testing is that it's done online, so while active. So it's at operating conditions, but it will not really experience the full operating conditions because we just partially move the valve for 5 to 10%. So it's not as strong of a, yes, it will be at operating condition, but it's not a it's not a full does the valve really close type of test. Does the proof test coverage affect both the SIL of the finite element as well as the SIL of the SIF? So the proof test coverage affects the average probability, in this case, the average probability of failure in the amount that we're calculating. And if I would have pointed out during the webinar, the results for the individual selections you can see up here. In this case, the proof test coverage for our finite element will change the calculated proof test coverage for our, calculated average probability of failure in the amount for our finite elements. But you will see that if we go to the different safety functions, that the top part, the sensor and logic solver, are pretty much unchanged. No, they are unchanged because the finite element proof test coverage doesn't impact the proof test coverage on the sensor. or the proof test coverage on the logic solver. So each has its own proof test coverage based on the failures that we can reveal during the test. How do we calculate proof test coverage? So in our case, what we do is we do a detailed analysis of a product. We look at all the dangers and detected failure modes, and then we look at the different tests, and then we determine, can a test reveal a particular failure mode? And if yes, then it's obviously covered. If not, it's not covered. And we kind of saw that. If I go back to the slides, we kind of saw that on this slide here, where we have a solenoid, if a particular functional failure mode, loss of drive for the entire final element assembly, has a total of dangers undetected failure rate of 230 fits, 230 times 10 to the minus 9 failures per hour. And then we can see what the coverage is, how many failures are detected by the test. And we can see that of the 230, 228 will be detected by proof test 5, and 207 will be detected by proof test 1. And detection divided by total will give you the proof test coverage. So we do that with a failure mode effect and diagnostic analysis, and see which particular failure modes of a device can be revealed with the test and which not. Another question here is, does tight shutoff impact proof test coverage? Yes. And that tight shutoff impacts the overall failure rate. If you have a scenario, and maybe we can see that actually in the tool. So let's go to that floating ball valve and look at its data sheet. And we have, yes, I can see both. So let me get the highlighter. Clean service, close on trip, full stroke, no partial stroke testing. We see certain coverage factors. And then clean service, close on trip, tight shutoff, and no partial stroke testing. So ignore the one in the middle here and look at the top one and the bottom one. And we can see that if you do if you just look at the failure rates, the failure rate of the clean service, close on trip, full stroke, tight shutoff is not needed to achieve the safe state, is 700 times 10 minus 9, or 700 fits. If we do need tight shutoff, then it's 1,700 fits. So it's significantly higher. Why? Seat issues are a problem now. In the first assumption here, we don't need tight shutoff. We just need to stop flow. Not the ability to not achieve tight shutoff is okay. It's tolerated. In this scenario, it's not. So apparently the failure rates go up. A partial stroke test will not test anything with regard to the seats. So you see that the coverage drops. If you look at the full stroke, sorry, we're talking about the full stroke. A full stroke test will not look at the seat itself. So you see that there's a significant drop in coverage. If we do a leak test, however, you can see that the leak test will detect a lot of those seat failures. So actually the proof test coverage goes up compared to proof test coverage for the normal operation, because now there's more failures to detect. So obviously if we look at one device, a higher proof test coverage will be better, more extensive to test. But if we look at two different devices, and in this case, yes, it's the same valve, but there's two different operating modes, doesn't necessarily mean that this higher proof test coverage will lead to a lower probability of failure on demand. But we can see that more failures can be detected, can be revealed if we do this more extensive test. And that kind of makes sense, because now the seats are an issue. So again, knowing the failure modes, we can see what can be revealed by a test and what not. Could we test a fine element more frequently than the rest of the SIF? Absolutely. But again, that goes into more corporate philosophy as to how you want to handle those types of things. Is there any recommended safety margin for PFD average? There's not, at least not that I know. One of the things that is required in the standard is that we use realistic failure rates, that we use certain confidence limits on failure rates, which is the case in our in the equipment in our database. So I'd say that if let's say I need to achieve a SIL 2 and I end up with a risk reduction of 101 in my calculation, then I would feel comfortable saying I've met SIL 2 because of the failure rate confidence level. So there's not a known, at least to the best of my knowledge, a safety margin that would be applied. Now, some companies do. Some companies apply a safety margin, and you can do that on the requirements end. And say, hey, I always want to, let's say my calculated risk reduction is 50. I'm going to ask for 70. You can implement something like that, which we support in the tool as well. My screen resolution is apparently a little bit high, and there's someone here that, and unfortunately I see this just now. Can you zoom in? I'll try to look at that for the afternoon webinar. I'm running a just a regular HD screen here, but maybe I can zoom in a little bit more for the afternoon webinar. All right. So I think that's all the questions. If I missed something, I'll let me know. You can reach me and my colleagues. Easiest is by looking at our knowledge database at support.exida.com, which specifically focuses on exSILentia. Follow us on one of these, Twitter, Facebook, Instagram, YouTube, LinkedIn. You can reach out to myself or just simply to info@exida.com with any additional questions. We have a couple of courses coming up. None are tool specific at this point, at least on the public schedule. We're looking at adding some courses. If you're interested in an exSILentia training course, either on the Silver or the LOPA or the PHA module, let us know, and we can work around your schedule to see what is your availability and host an open enrollment class. We do have online self-paced training or on-demand training, and we do have the exSILentia SIL verification and layer protection analysis tools available there as online offering. Actually, the latter one, the layer protection analysis with exSILentia training course, that is brand new. I'm not sure if it's already available to order on online, but if you're interested in that, reach out to us at info@exida.com, or just go through the online training link here, and you can one of our training coordinators can get in touch with you. So with that, we've reached the end of the webinar, and the recording will be made available on YouTube later this week. I assume later this week, otherwise early next week. It's already Thursday, yes, so that will be available, and I think slides are also being shared with you, at least a handout at the end of the webinar. So there's a second recording this afternoon, and after that, that information is shared. So thank you all very much for attending, and I hope this was informative, and hope that everybody can use these new functionalities, these new features that we've introduced in the exSILentia software. So thank you very much for dialing in, and I'm going to stop the recording now, and appreciate your time, and take care. Bye-bye.